Let's start fairly simple. Binary logic is a system based on two states, hence the name binary. One, which could be interpreted as true or sometimes on, and zero, which can be interpreted as false or sometimes off. And that zero basically means like false, as we've talked about, or sometimes in a circuit, it can just mean no voltage. If you pass no voltage, you're actually in a zero state. The one can actually just mean true. A value can be true, or sometimes it can refer to a state where you have high voltage, you pass a high DC voltage in a circuit. Turns out you can combine all of this and create logic gates, electrical components which take inputs and map some rules to get a particular output. And those rules that you can program, they actually called logic gates, and they're actually made up of transistors. An easy example to understand this is, imagine you're passing A is equals to 0, no voltage, B is equals to 0, no voltage. That whole system you're seeing over there can result in X being equal to 1. Those green and red things that you're seeing are actually called transistors. They govern this rule that made this possible. In a lab, you might see this, where A is just a pin, and B is another pin where you pass in voltage, and X is another pin which you can measure the voltage that you get out, and that's a logic gate. We're going to start off with an OR gate, and bear in mind, logic gates are just combination of transistors that result in a particular outcome. So if you start with A and B and X, certain combinations of A and B will result in a particular value of X. And you can summarize all of these ideas in a table that is known as a truth table, a table of truth, or true or false values. So it starts off with A, B, and then X. Some textbook might say F in place of X, or some may just say X is equals to A or B. I'm going to keep it as A or B. So you start off with 0, and then 0, and you get 0. And 0 and 1, that is A or B, with B being equal to 1, gives you a 1. A is equals to 1, with B equal to 0, that gives you 1, because A is actually 1. And if A or B, one of them is 1, you get an X, which is 1. So that's a truth table. And turns out you can write an equation, X is equals to A plus B, so that plus in the middle refers to OR. So OR, A or B, A plus B. And you can look at the outcomes now. So 0 or 0, 0 plus 0 is 0, 0 plus 1 gives you 1, 0 plus 1 gives you 1, 1 plus 1 gives you 1. And I can remove the plus and put an OR in the middle. A fun example, imagine you're only happy if you graduate, or plus if you start a startup. So that's when you're happy. So you're happy if you start a startup, or if you graduate, or if you do both, but you're quite sad if you don't do either of the two. So that's an OR statement, either or, this or that. I like to explain this using circuits. This is by no means what an OR gate looks like, but I think it just helps you understand the logic behind OR gates more intuitively if you use circuits to understand them. So imagine this instance where you have two switches that are open. So it's going to be off, nothing is going to flow through because, well, both of them are off. But if you were to do something interesting and flicker one of the switches, so close A is equals to 1, and current now flows through, you can see that the light turns on. So X is equals to 1, the desired outcome is seen. You can flip the logic around. If you close B is equals to 1 and A is equals to 0, current will actually flow through B is equal to 1, and the light bulb will still be on because one of those switches is on. A or B is actually on. If you close both of them, A is equals to 1, B is equals to 1, current flows through both, and the light bulb will always be on. So the light bulb is always on in cases where one or both of those are closed. The next is an XOR gate. The X, as you can see over there, stands for exclusive. Think of exclusive as what it actually means. Imagine you're in a relationship. It only means that, you can date Mary or you can date Sarah. You can't date both at the same time. You can't have two people at the same time. That's what it means to be exclusive. Visually, the symbol looks like an OR gate, but it just has that weird line at the back. As per usual, if both are 0, you get 0 out. If one of them is a 1, you get a 1 out. If both are 1, you get a 0, exclusive. And that's an XOR gate. You can also draw a truth table as per usual. Same logic, you can put 0 and 0, so that gives you a 0, and a 1 is effectively going to give you a 1. If A is 1, and B 0, that effectively gives you a 1, and if both of them are 1, you can't have both with an exclusive case, so you get a 0 out. The equation looks like an OR equation, but it has that little circle around the plus, so that's an exclusive case. And if you see that, for example, if you say 0 exclusive plus 0 gives you 0, 0 and 1 gives you 1, 1 and 0 gives you 1, but because it's exclusive, you can't have both, you get a 0 for 1 and 1. The next gate we can make is called an AND gate. A gate, remember, these are just a set of rules that explain what happens between inputs and outputs. So for an AND gate, if both of the inputs are high, that means A and B are just 1. That's the only case you can expect to have an X that's a 1. For the other cases, it's going to be 0. We can draw a truth table, as always, to summarize all the cases as below. For all the 3 cases, it's going to be a 0 because it's not A and B. It's only the last one where we get an X, which is 1. We can create an equation as well. The dot in the middle over there, that means AND. So A times B, A and B. That's what the full equation for an AND expression looks like. And the same can apply. 0 and 0 gives you 0. 0 and 1, 0.1 gives you 0. 1 and 0 gives you 0. Only 1 and 1 can give you a 1. And as always, remember the dot means AND. And, no pun intended, we can also understand an AND gate using this circuit setup. Remember, this is not how the circuits are arranged. It's usually a bunch of other complex circuit components. This is just to improve your understanding. So if both of them are open, we're going to have off, because you see current can't flow through open switches. But you can have something interesting. You can close one of the switches, so B is equals to 1. You close that, you still see that our current cannot move and proceed to follow through. The electrons can't really just flow through to get to the bulb. If you were to close A, so have A is equals to 1, but actually open up B, you realize that electrons can now flow through, but they can't also reach the bulb because B is equals to 0. So in all of those 3 cases, because your switches are connected that way, you can't get an output. But if both are 1, finally electrons can flow through the entire circuit and it's going to be on. So it's only going to be on for cases where A and B are equal to 1. The next gate is my personal favorite, the NOT gate. It goes against convention. Now, what it does is actually kind of crazy. If you give it A, it opposes it. You give it A is equals to 1, it gives you 0. You give it A is equals to 0, it gives you 1. You're like, what do you want, right? So we can do a truth table for this. So what it means is you give in high voltage, you get nothing. You give nothing, you get high voltage out. It's kind of crazy. So that's the truth table. If we have 1, we're going to get 0. And it's quite easy. For the equation, you just put that little dash on top. That just means not or inverse. And the logic is very simple. For x is equals to 0, that's because A was 1. For x equals to 1, that's because A was 0. Okay, the next gate is the NAND gate. Think of this as the AND gate's older brother, right? So it opposes what the AND gate just does. Wherever you had, an X for the AND gate, is going to be the opposite of that for the NAND gate. So that means when A is equals to 1 and B is equals to 1, you get a 0. The rest, you get a 1. The truth table is very simple. Remember, the whole goal is NAND, so it's not A and B. So for X, it's going to be X is equals to not A and B. So for 0 and 0, you're basically going to get a 1, because for A and B, you would have gotten a 0, but you're supposed to get a 1, the opposite. 0 and 1 gives you a 1. 1 and 0 basically gives you a 1. That's the opposite for an AND. And for 1 and 1, you're now going to get a 0, because AND should have given you 1. The opposite of that is going to be a 0. As per usual, the dot in the middle, that is over there, basically refers to AND. And the line that's over there at the top basically means inversion. So not whatever you're going to get for A and B, take the opposite of that. So easy example, 0 and 0 gives you 1, because there's a not at the top. For 0 and 1, not, that gives you 1. 1 and 0, not, gives you 1. And 1 and 1, not, gives you 0. That's opposite of the AND gate. It's flipped. So not 0 and 0. So the other one is not 0 and 1, that's 1. The other one is not 1 and 0, that gives you 1. And the last one is not 1 and 1, that gives you 0. It's just the opposite of the same logic that you used for the AND gate. Okay, and for our second setup, remember, this is not the setup for a NAND gate. It's just a way to help you better understand this visually. I think it's more intuitively easier to understand this using these cases. Okay, so it's going to be on. If A is equals to 0 and B is equals to 0, it's going to be on. Because you can imagine that current is going to flow throughout. It doesn't move through because those 2 switches are open. If you close one of them, it's just going to keep on moving. So it's going to be 1 throughout all the cases, because it's just going to flow quite easily. And if you do something very fun and you close B, but you open A, it's just going to keep on moving, right? Nothing. It's just minding its own business. But it's only where you have A and B, so not of that is going to be 0. That's when both of them are closed and current just flows through there and it never reaches that light bulb. So this is a way in which you can understand what's sort of visually happening when you try to toggle and switch values for A and B. The NOR gate is basically the OS gate or the brother. So effectively, it's going to be the same setup, but it's only going to be 1 for 0 and 0, the opposite. So that's the only case we're going to get an X equals 1. For the rest, we're basically going to get 0. no matter how you change A and B. It's important to note that the circle that you're seeing over there, that circle basically means inversion, right? So you've seen it on the NOT gate, you've seen it on the NAND gate, you're now seeing it on the NOR gate. As for the truth table, it's kind of similar to the OR gate, but just a little bit different. So it's now for X is equals to not A or B. So it's going to be a string of zeros throughout, except for the case where we have 0 and 0, where we're going to have 1. For the other cases where you have A or B, you're not supposed to get any output for that because there's a NOT. For the equation, same. The plus, as always, just refers to OR. That's good. But the slash on the top here, that's going to be for NOT or mean inversion, right? So the same logic, you can basically accept that 0 plus 0 with the dash on top means 1, and 0 plus 1 with the dash on top means 0. So for any combination, you're going to get a 0 effectively for each to kind of make sense. Okay, the same is going to happen for our second setup, right? So for a NOR gate, the setup is kind of similar. So to try and understand it, we're going to leave our switches like that. Both of them are open, so you can see that current sort of flows around. There's really no way it can move through both of those guys because effectively both of them are open. If you close A, current is now going to flow through there, return back, so it's never really going to reach that other side. So, you know, if you were to close B and open A, current flows through again, never really reaches that side. So you're only going to get one in one specific case, right? If you were to close both, current is going to have a short path to just return back to the output. So this sort of helps you understand how a NOR gate might work intuitively. The buffer gate is kind of boring. Like what you put in is what you get out. You know, you could amplify the signal. Like if you put in A is equals to 1, or A is equals to 0, you get X equals to 0. Put in A is equals to 1, you get X equals to 1. It's very boring, right? Even the truth table for a buffer gate is kind of simple. But we sort of use them, you know, to amplify signals or to do other cool stuff with the signal. But you know, what you get in is effectively what you get out, and that's kind of life. It's just like that. The XNOR gate is like an XOR gate, but with just a NOT at the top. So A, B, and X, but a NOT. So you take the XOR truth table and you just change the zeros into ones and change the ones into zeros. That's basically what the NOR part does. So not an XOR gate. That's what it is. It's not an XOR gate. So when A is equals to 0, B is equals to 0, you get a 1. A is equals to 1, 0, both are 1, you get a 1. And then A is equals to 0, you get a 0. But for it to make sense, we're going to redraw the truth table again to make it a bit more explicit. So in a similar manner, you draw your lines. You have A, B, X is equals to A, X, NOR, B. So when you have 0 and 0, you get a 1. When you have 0 and 1, you get a 0. You'd have gotten a 1 for an XOR table, because it's like an OR table. So you 1 and 0, you also get a 0. It's supposed to be exclusive for an XOR, but it's not going to be exclusive. So it's going to have 1, 1, and 1. And that's all that I have for you guys when it comes to understanding logic gates. I hope this helped improve your understanding of this gate a little bit better.